Hi. In the second part of this lecture, we are going to look at an example of the ideal vapor compression refrigeration cycle. In this example, the refrigerant R134A is the working fluid. The refrigerant leaves the evaporator at minus 20 degrees Celsius. So this is point number 1. The evaporator exit and has a condenser pressure of 0.9 megapascal. So this is the condition in the condenser here, P equal to 0.9 megapascal. The mass flow rate of refrigerant in this cycle is 3 kilogram per minute. So this is m dot. Okay. We want to determine the COP of this refrigeration system and compare with the COP of the reverse Carnot for the same maximum and minimum temperature operating in this system. And finally, we want to determine tons of refrigerations. Okay. Now in these problems, we are considering an ideal VCR. So when we talk about ideal VCR, we have to know automatically by ourselves that number 1 would be the sat vapor. Number 1 would be on the sat vapor line. And also number 3 here would be the sat liquid. It is on the sat liquid line here. So this is the ideal VCR system. Okay. The cycle consists of isentropic, which is process 1-2, isobaric, which is process 2-3, isenthalpic or process 3-4, and isobaric in process 4-1. Okay. Now, we can obtain the property parameters or the property data by using the refrigerant table, or we can also use the thermodynamics diagram, such as the pressure and the enthalpy diagram. Okay. Now you can locate the cycle on this pH diagram as well. If you start from point number 1, which is at minus 20 degrees Celsius, you can see that you have a constant temperature line, minus 20 degrees Celsius, which is this line. Okay, this is the constant temperature line. Okay, so point number 1, which is at minus 20 degrees Celsius, it is also sat vapor, so it is this point. Now in the first process, which is process 1-2, which is isentropic, it will follow an isentropic line. Isentropic line would be line like this. Okay, you can see constant entropy line. Okay, constant entropy line like this. So process 1-2 would be following this one, this line. So we start from minus 20 degrees Celsius sat vapor. We follow the isentropic line to the pressure of 0.9 megapascal. This is 0.9 megapascal or 8 bar. Okay, 9 bar. 0.9 is 9 bar. And on your left axis, it is 0.9 megapascal. Okay. Now you enter the condenser, it would be isobaric. It would be condensed to the sat liquid. Okay, so the part will move horizontally to the sat liquid line, this one. Okay, and then it will flash through a throttling valve. It will move down in a vertical direction. So it will move down, which is process 3-4, move down to the sat condition in the evaporator again at minus 20 degrees Celsius. Okay, pressure may be around 0.1, say maybe 1415 megapascal, and then it will enter evaporator here at this point, and then it will be vaporized to become sat vapor again. So that will complete your ideal VCR here. Now, by plotting the process change on the pH diagram, you can easily locate it, or you can easily read the value of enthalpy at every point. Enthalpy at number 1, 2, 3, and 4 can be read from x-axis easily. Okay. Now, if you do the analysis by using the data from the pH diagram, you have to use all value on that diagram. Okay. On the other hand, if you choose to use the data from the property table, you have to use all data from property table as well. You must not mix the data between different sources. For example, if you take enthalpy from some point from the diagram and the other point from the property table, that would be a big mistake. Okay, the result will not be correct one. Okay, so you must be aware of the consistency of the data source that you are using. Okay, you should not mix them. Okay, all right. Because the reference value from different sources are different. Okay, the reference value of enthalpy from different sources are different. So you should be very careful about this one. Okay, in this example, I'm going to use the data from the refrigerant R134 table. Okay, I did not use the data from the pH diagram that I have shown you before, but I've just shown you to understand that we can use the data from the diagram as well. Now, from the refrigerant R134A tables, at state number 1, you know the temperature and you know that it's sat vapor. So this state is fully defined. You can go to the saturated table, okay, to look at the enthalpy and entropy value. At state number 2, when you follow the compression process, okay, you know the pressure, which is the final pressure, and you know that the process is isentropic, so you know the entropy value at the exit as well. Okay, so S2S equal to S1, which is 0.946. Okay, so state 2 will become fully defined from the isentropic relationship. Having known the pressure value and entropy value, you can use the superheated table. This must be superheated now. Superheated table to determine the enthalpy value and the temperature value at the compressor exit. Okay, so here in the example, I've just shown you the result, enthalpy and temperature at the compressor exit. At state number 3, because this is ideal VCR, you know the pressure and you also know that at this condition it is sat liquid. So state number 3 is now fully defined. You know 2 pieces of information. You can just go to the saturated table to determine the enthalpy, okay, enthalpy of the sat liquid, okay, and you can determine the entropy as well, okay, of the sat liquid. All right. Now at state number 4, you know that it is the total exit, okay, from the JT expansion. So you know that the final temperature is at the saturation temperature, or T4 equal to T1, And you also know from the JT expansion that the enthalpy would be constant. So H4 equal to H3. Okay. So from this condition, you can also determine the vapor fraction at the valve exit here. Vapor fraction you can determine from you can say X4 equal to H4 minus HF divided by HG minus HF. Okay, HG and HF is at minus 20 degrees Celsius. Okay, so you can see that at this point you have some vapor generated and the vapor fraction is 0.358. Okay, and you can also calculate the entropy as well. Entropy at the valve exit S4 can be calculated from X4 Sg plus 1 minus X4 SF. Okay, so you can see that the result would be 0.4053. Okay, when you compare the entropy value between the valve inlet and the valve outlet, you can see that you have entropy increase. Okay, so it is clear that the JT expansion is a reversible process. Okay, you have entropy increase. S4 is greater than S3. Okay, you have entropy increase for JT expansion, but the enthalpy would be constant. Okay, so from the property determination, you have evaluate all enthalpy values, enthalpy at every point. You can then do the energy balance in each process to determine the work transfer or the heat transfer in each process now. Okay, so you can calculate the COP of the refrigeration system here. COP of refrigeration system is QL divided by W net in. QL you obtain from the heat balance in process 4.1, that would be m dot multiplied by H1 minus H4. W net in can be determined from the energy balance in process 1-2, that would be m dot multiplied by H2 minus H1. Okay, since the flow rate in both processes are equal, so they can be cancelled out. You know enthalpy at every point. You can just substitute them and calculate the COP of this ideal VCR system. That is 3.44. Now, if we want to compare with the COP of the reverse Carnot operating between the same maximum and minimum temperatures, okay, we can use this equation for the reverse Carnot. COP of the reverse Carnot is TL divided by TH minus TL. Okay, temperature here must be absolute temperatures. So you change the temperatures, okay, TL minus 20 plus 273. Down here it's a temperature difference, TH minus TL. So you don't have to add 273 and then subtract it again. The difference in Kelvin is equal to the difference in Celsius. So you can just substitute the Celsius value here. Okay. So the maximum temperature is point number 2. Is at point number 2, T2. Okay. So we have already calculated T2 is 43.79 degrees Celsius. TL is minus 20 degrees Celsius. So we take the difference between them, and that would be similar to the delta in Kelvin. So COP of the reverse Carnot operating between the same temperature range here would be 3.97, which is greater than the COP of the ideal VCR that we have considered here. Okay. Now for the last question, we want to determine the tons of refrigeration, okay, or we often call it as the cooling load or refrigeration effect. So QL is the amount of heat that we want to remove from the cold refrigerated space. It can be calculated from the mass flow rate multiplied by H1 minus H4. Okay, here M multiplied by H1 minus H4. And then we use a conversion factor to convert from kilojoule per minute into tons of refrigeration. So we use this conversion factor here. So the result, the cooling load that we can obtain would be 1.94 tons of refrigeration. Okay, so this system can deliver or will have the refrigeration capacity of 1.94 tons. Now we also have another measure of the effectiveness, okay, of the refrigeration cycle. Instead of using the COP, because COP is just a number values without any unit, okay, we might be wondering how good it is for any particular number. Okay, we don't know whether 3 is good enough or 4 is good enough. We may then use the other terms to just explain the effectiveness of our refrigeration cycle, which is the power requirement, okay, power requirement for each ton of cooling, okay, power requirement for each ton of cooling. So the power requirement for each ton of cooling is actually W net required divided by QL, or it is actually 1 over COP, okay, 1 over COP. But we want to convert the unit here into the horsepower per ton of cooling, okay, so we use the conversion factor of 4.715 horsepower per ton of cooling here, multiplied by 1 over COPR. Okay, this is your conversion factor. Okay, so the result, it would be 1.37 horsepower per ton. Okay, so with this number, it would be more meaningful. Okay, it means that you will need 1.37 horsepower, okay, to supply your compressor in order to get 1 tons of cooling services. Okay, that would be more meaningful in this case instead of using COP. Okay, so this is another measure that you can use to tell whether your refrigeration system is effective or not. Okay, and that would be the end of this example for ideal VCR. See you next time for the actual VCR.